The objective of this lecture is to provide a discussion of the first part of non-coplanar, impulsive orbit transfer. So this is part 1. Now, the key results that are going to be developed in this lecture are as follows. Is that first we are going to define what is called a cranking impulse. And a cranking impulse is one that changes the plane of an orbit. That's the first thing that we're going to define. The second thing that we're going to define is, or describe, is we're going to describe the relationship between what's called the cranking angle and the change in orbital inclination. And the third thing is we're going to develop the condition for when the cranking angle is the same or is equal to the change in the orbital inclination. And we're going to do this under the stipulation that we're dealing with circle-to-circle transfers. So the transfer is going to be circle-to-circle. We're not going to be dealing with any elliptic orbits. We're going to be dealing purely with circular. So this is a circular orbit to circular orbit, if you want to write it that way. Circular orbit to circular orbit. But these two circular orbits are not going to be in the same plane. So this is important, is that the two orbits are not in the same orbital plane. So we're going to start this process off with the following with the following concept, which is what is a cranking impulse. So let's talk about a cranking impulse. So that was the first thing that I said we were going to describe. So here is a cranking impulse. Now, in order to define a cranking impulse, consider the following pictures. So consider a spacecraft moving on an orbit with an inertial velocity VI minus. And at some point on the orbit, or at this point, I should say, on the orbit, an impulse delta VI is applied that changes or rotates VI minus to VI plus. And finally, assume that the magnitude of VI minus is equal to the magnitude of VI plus. And we're just going to call that V. So what this picture looks like is as follows, is that we have this velocity VI minus, and this impulse is applied that results in this new velocity, which I'm going to call VI plus. And there's an impulse delta V that takes me from VI minus to VI plus. So this impulse here is delta VI. And it's important that you understand that the magnitudes of these of the pre-impulse and post-impulse velocities are both V. So this magnitude is V, and that magnitude is also V. Now I'm going to define the angle between these two vectors, VI minus and VI plus. I'm going to define that angle as theta. So theta is what is known as the cranking angle. And delta VI is what's called a cranking impulse. So we've now defined what that means. Now what is really important about a pure crank, this is what's also called a pure crank, is that because the magnitude of VI minus is equal to the magnitude of VI plus, which is equal to V, that implies that the energy before the impulse is applied has to equal the energy after the impulse is applied. So this is the specific mechanical energy, which means that the specific mechanical energy does not change due to a pure crank. This means we're not actually elongating that velocity V plus relative to V minus. They're the same because I just said that their magnitudes are the same. And the reason that it doesn't change the orbital energy is because the position doesn't change across an impulse. So I can add that if it makes it a little bit more complete. Specific mechanical energy does not change due to a pure crank because the magnitude of VI plus or the magnitude of VI minus is equal to the magnitude of VI plus, and position does not change due to an instantaneous delta V. So it's not possible for that to happen because the mechanical energy, if you remember the specific mechanical energy, E is equal to V squared over 2 minus mu over R, and the velocity has the same magnitude, so V minus squared is equal to V plus squared, and R can't change, so R minus, if you want to think of that, is equal to R plus, which means E minus has to equal E plus. So the specific mechanical energy does not change. Now, let's look at this diagram then a little bit more carefully. Let's make it a little bit bigger so we can actually figure out what the amount of this delta V is. So I have a crank in the amount of delta V, So here's my crank. It's my cranking impulse. Here's my cranking angle, which you can see that the cranking angle, because these two sides of this triangle are both V, if I break this up by dividing it exactly in half, and I put theta over 2 in one half, let's move it a little bit closer, theta over 2, and theta over 2 in the other half, the full angle is, of course, theta. But if I do that, then first is that this triangle, this is an isosceles triangle. So because it's an isosceles triangle, when I bisect the side, the angle that forms due to the bisection, that's a right angle. So now what I can do is I can take one half of this triangle, it doesn't matter which one I can take either half, and I can put it down here, and I can write down that this right triangle construction where this angle here is theta over 2 and the hypotenuse is V, and the impulse has been split in half. So this impulse here is delta V over 2. Because remember that this magnitude going from here to there, that magnitude is, if I move this just a little bit, this magnitude is delta V, right? So that becomes delta V over 2. So as a result, I can actually just do the simple trigonometry on this, which is that then sine of theta over 2 is equal to the opposite side, but the opposite side is delta V over 2, all divided by the hypotenuse, which is V. So that implies that delta V over 2 is equal to V times the sine of theta over 2, which implies that delta V is equal to 2V times the sine of theta over 2. So this is a cranking impulse. That's the definition of a cranking impulse. Theta is the cranking angle, and delta V equals 2V times the sine of theta over 2 is the cranking impulse. Now you can see that a cranking impulse is very, very inefficient for a spacecraft in orbit. So a cranking impulse is very inefficient. Why is it inefficient? Well, it's inefficient because its magnitude, or its, I should say its size, depends upon the velocity, or I should say the speed, of the spacecraft. Now, if a spacecraft is moving with a very large speed, if I want to rotate that velocity by a large angle, say for example theta is equal to 90 degrees, I want to do a crank of 90 degrees, this is going to be a very large number if the spacecraft is moving with a large speed, and it could very well be moving with a large speed because I could be in a low Earth orbit where the spacecraft velocity or spacecraft speed is large. So it's not a very efficient process, but it is the simplest way to actually be able to rotate the orbit plane. But what's really important now is that we know it's inefficient, but what we also have is we have a simple construct which allows us to be able to rotate the orbit plane given an angle theta, which is my cranking angle, and it results in a value delta V. So what we're going to do now is we're going to actually do some calculations to try to understand the relationship between the cranking angle and the orbital inclination. So this is an important construct here. This is really important because it seems as if these two things should be the same. The cranking angle is not equal to the orbital inclination, or just say the change in the orbital inclination. Now you'd think it might be, because you'd say, well, if I rotate the velocity by the the amount theta, then I should rotate the inclination. I should change the inclination by the amount theta. But that's not actually how it works. So what we're going to do now is we're going to derive the relationship between the cranking angle theta and the change in orbital inclination delta I for the case of a circle to circle orbit rotation. So here's what this picture looks like. So we're going to start with this diagram. This diagram is going to get messy real fast, so I've got to be real careful as to how I draw this diagram. But here is the diagram with the three directions. These are the planet-centered inertial coordinates, and they are IX, IY, and IZ. Now, I'm going to superimpose on this picture two orbits, but in order to be able to see the orbits clearly, I'm going to kind of draw this sector of a sphere to be able to make it a little clearer what's going on. So right here, this is the equatorial plane. And imagine that I have a circular orbit. So here's my circular orbit. Circular orbit kind of crosses through this that way. So this is my first orbit. And that first orbit has an orbital inclination, which I'm going to call I1. So I'm going to draw this picture. Here's my specific angular momentum, H1I. And this angle is I1, which is the orbital inclination for that first orbit. Now I have a second orbit. Now that second orbit has a larger inclination. It could have a smaller inclination, it doesn't matter, but I'm going to do it with a larger inclination. And it's going to be drawn as I show here. I want to make sure that it's not too extreme, so I want to keep it somewhat reasonable. There's the second circular orbit, and it has a specific angular momentum, which I'm going to label as H2I. So as a result, I have a second inclination, which is I2. Now, the angle between H1 and H2 is this angle theta, which is this cranking angle. But if you look at the picture, you'll actually see that there's a little bit more going on in this picture than meets the eye. But the two key points that we need to focus on are the two ascending nodes of these two orbits. So if I draw the line of nodes for the first orbit, there's the line of nodes for the first orbit. So this is N1. And here is the line of nodes for the second orbit. I'm going to call it N2. Now, if you examine that, that means that the angle between Ix and N1 is omega 1, which is the first longitude of the ascending node, and the angle between Ix and N2, that's the second longitude of the ascending node. Now this picture in and of itself isn't really all that useful. We have to draw some two-dimensional pictures in order to make this a lot clearer as to what's going on. We're going to start with this with a three-dimensional picture, but we're quickly going to now move on to two-dimensional pictures. So imagine that I look down on the equatorial plane. So I'm looking down on the equatorial plane now. Okay? If I look down on the equatorial plane, then the direction here, this is IX, and this direction is IY. So if I draw those two lines of nodes, there's the first line of nodes, which is N1, and there's the second line of nodes, which is N2. Now those are the same lines of nodes that I have in this previous picture here. There's nothing different about them. It's just the perspective has changed. Now what I'm going to do is I'm going to draw the direction minus IY. So this is minus IY. And on this picture, I'm going to put two other vectors. And these two vectors are going to be called M1. So this is M1. And this other vector is going to be called M2. So to be careful about it, I'll make it a little bit longer. M2. Now, what's important about these two vectors is I'm going to assume, even though the lines of nodes are not unit vectors, so N1 and N2 don't have unit magnitudes, I'm going to make M1 and M2 be orthogonal to N1 and N2 respectively, such that they're both unit vectors. So we're going to say the magnitude of M1 is equal to the magnitude of M2, which is equal to 1. And it's also going to be the case that N1 dotted with M1 is 0, and N2 dotted with M2 is also 0. That just makes them orthogonal to those lines of nodes. Now what we're going to do is we're going to draw two other pictures, which is that if you were to look down on this orbit plane, these two angular momenta are actually kind of sitting up above this orbit plane. So I'm going to actually draw those two pictures, which is that if I draw the cross section of the direction, so remember this direction right here, this direction is IZ. So if I draw the M1 IZ plane, I'm going to draw that over here, then this direction is M1 and that direction is IZ. And H1 is in this plane. It has to be in that plane because H1 is the projection of the vector H1 projected onto the direction M1. That's how I got M1. And similarly, I've got this picture for the second angular momentum, which is that I've got IZ, and I have M2, and then I have the second angular momentum, which is drawn here. That's H2. Now the angle from IZ to H1, that's I1. The angle from IZ to H2, that's I2, because that's the definition of the orbital inclination. It's the angle between IZ and H. And from this, I can now construct the two angular momenta, which is that I can actually write them in terms of IX, IY, and IZ. So what we can do is we can see that H1 is equal to its magnitude, H1, times the sine of I1 times M1 plus the cosine of I1 times IZ. Similarly, H2 is equal to the magnitude, H2, times the sine of I2 times M2 plus the cosine of I2 times IZ. But we know from the diagram, if we go back over here and we look at the diagram, we see that M1 is equal to, well, it's equal to, well, now let's put angles here. So this angle is omega 1, and this angle here is omega 2. Similarly, this angle is omega 1, and that angle is omega 2. So what I've got is I've got the cosine of omega 1 times minus Iy plus the sine of omega 1 times Ix. So m1 is equal to minus the cosine of omega 1 times Iy plus the sine of omega 1 times Ix. And similarly, m2 is equal to minus the cosine of omega 2 times Iy plus the sine of omega 2 times Ix. So now if I put this in the order Ix, Iy, Iz, this gives me that m1 is equal to sine of omega 1 times Ix minus the cosine of omega 1 times Iy, and m2 is then equal to the sine of omega 2 times Ix minus the cosine of omega 2 times Iy. And if I substitute those results back in to the two angular momenta, I get h1i is equal to h1 times. Now I've got sine of I1 times sine of omega 1 times Ix minus the cosine of omega 1 times Iy, and then plus the cosine of I1 times Iz. And then h2i is equal to h2, which is its magnitude, times sine of I2 times sine of omega 2 times Ix minus the cosine of omega 2 times Iy, and then plus the cosine of I2 times Iz, which I can expand out, and I will get the following result. So therefore, h1i is equal to its magnitude times, well, if I expand this out, I get sine I1 sine omega 1 times Ix, and then I get minus sine I1 cosine omega 1 times Iy, and then I get plus cosine of I1 times Iz. Now the same thing goes for the second specific angular momentum. I get h2 times sine of I2 times sine of omega 2 times Ix and I get minus sine of I2 times cosine of omega 2 times Iy plus cosine of I2 times Iz. Now, remember that what we're trying to do here is we're trying to derive a relationship between the change in orbital inclination or if I say it in the same order, as I said it before, I'll do that. I'll say the cranking angle and the change in orbital inclination. So you can see here that we have things in terms of the orbital inclination, but we don't have anything in terms of the cranking angle. So remember, we also said that this was going to be done for circle-to-circle transfer. So both orbits are circles, are circular, of the same size. So if that's the case, then we know that the magnitude of h1i has to equal the magnitude of h2i, which is equal to h. Which means that essentially we're eventually just going to be able to eliminate h from this whole problem. But both of these can be replaced with just simply h. So if I take these two angular momenta, let's suppose we compute now the dot product h1i dotted with h2i. Let's compute that dot product. So now we're using this fact. We're going to use this fact in here. So we're going to take the fact that these two angular momenta are the same, and we're going to use that fact in here. So we then we obtain the following result. That h1i dotted with h2i is equal to h squared, because both magnitudes are h now. And now let's just start multiplying through. We get sine of I1 times sine of omega 1 times sine of I2 times sine of omega 2. That's multiplying those together. And then I get plus sine I1 cosine omega 1 let's write this just a little bit smaller. So we get plus sine I1 cosine omega 1 sine I2 cosine omega 2. That takes care of those because the negative signs cancel out. And then I get plus cosine I1 cosine I2, which gives that h1i dotted with h2i is equal to h squared times. Now, you'll see in the first two terms that I have a sine I1, sine I2, so I'm going to factor that out. Sine I1, sine I2. And what I'm left with is, I'm left with sine of I1, say sine of omega 1, sine of omega 2, and then I get plus cosine of omega 1 cosine of omega 2 plus cosine I1 cosine I2. Now, if you look back, you'll see that when we did this whole calculation, we actually wrote everything out originally in terms of this basis ix, iy, iz. When I take the dot product, I'm just multiplying the respective components by one another and then just adding them up. That's all I'm doing. So that's how I wound up getting these results. So now I can actually take this result and I can simplify it a little bit more, which gives me that h1i dotted with h2i is equal to h squared. Now you see the term in the parentheses just becomes cosine of omega 2 minus omega 1. And then I get plus cosine I1 cosine I2. So that's the result that I get. But we also know that h1i dotted with h2i has to equal the magnitude of h1 times the magnitude of h2 times the cosine of the angle between them, which is the cranking angle. But that's just equal to h squared times the cosine of theta. So we can set these two things equal to each other. So we have two expressions. We have h squared times sine of I1 times the sine of I2 times cosine of omega 2 minus omega 1 plus the cosine of I1 times the cosine of I2 equals h squared times the cosine of theta. So the h squared, of course, cancels out, which then leaves us that sine I1 sine I2 times cosine of omega 2 minus omega 1 plus cosine of I1 cosine of I2 is equal to the cosine of theta. So now there's the relationship that actually tells us how the cranking angle affects the inclination. So this relationship tells us this is the relationship between the cranking angle theta and the two inclinations I1 and I2. But we're not interested in just that. We're also interested in when is the cranking angle equal to the change in the orbital inclination. So that's the question that we were trying to ask right at the beginning. So recall that it is of interest to know when the cranking angle is equal to the change in the orbital inclination. So let's suppose now that we look at the following condition. Suppose that omega 2 is equal to omega 1. What does that mean? That means that the two longitudes of the ascending nodes are the same. What it means in the diagram is that this picture actually simplifies tremendously. So this means that N1 has to equal N2, the two lines of nodes. Two lines of nodes are the same. So if I look at that on the diagram, let's go back to this diagram. The picture actually simplifies to the following, which is that here's my sort of 3D view of this whole thing. And it means that if this is the first orbit, so there's my first orbit, that's my first circular orbit, it means that the second circular orbit crosses the equatorial plane at exactly that same point, right? This is really important because N1 has to equal N2. So it means that the two ascending nodes are exactly the same. So this is really important. It means that the ascending node of both orbits are the same, are equal. So as a result of that, if you go back over here and we substitute in omega 2 equals omega 1, what that means is that omega 2 equals implies, or it's the same thing as saying omega 2 minus omega 1 equals 0. So now let's go back and let's substitute. If we substitute that condition in, then what does this last result that we got, which is the relationship between the cranking angle and the two inclinations, that simplifies. So then the last result becomes, or I should say simplifies to, well, we get sine of I1 times the sine of I2 times the cosine of 0 plus cosine I1 cosine of I2 equals the cosine of theta. So as a result of that, the cosine of 0 is 1. So this gives that sine of I1 sine of I2 plus cosine I1 cosine I2 equals the cosine of theta. But this equation that I have on the left-hand side just says that the cosine of I2 minus I1 which is equal to cosine I1 cosine I2 plus sine I1 sine I2 equals cosine of theta, which implies that I2 minus I1 is equal to theta. So this is a key result, which is that the cranking angle that rotates a circular orbit to a new circular orbit is equal to the change in the orbital inclination of the orbit only if the crank is performed at the ascending node of the orbit. So if I apply that crank anywhere other than the ascending node, then theta is not equal to I2 minus I1. So this is really important. So if the crank, we should say the cranking impulse, is applied anywhere other than the ascending node of the orbit, then theta is not equal to I2 minus I1. If the cranking impulse is applied at the ascending node of the orbit, then theta is equal to I2 minus I1. And that's really important because if you apply the cranking impulse at the wrong point, it's a less efficient crank. So you want the crank to equal the change in orbital inclination. So it's desirable that theta equals I2 minus I1. But that theta is most often not equal to I2 minus I1 because it is the case, it is generally the case that the cranking impulse is not applied at the ascending node. Now, you might ask the question, well, why don't we just always apply it at the ascending node? Well, in the case of a circle-to-circle transfer, we can often apply it at the ascending node, but we sometimes can't do it for timing reasons. We may need to do something else, but the bigger reason is actually that we're not always just applying a pure crank. So that's actually what is the next topic in the next lecture, which is that we're actually often doing an impulse that rotates the plane of the orbit and actually changes the orbital energy at the same time. Notice that in this case, we did not change the orbital energy. The orbital energy is the same before and after the cranking impulse is applied. But if we are actually changing the orbital energy, it actually is not always possible if we're going to do this in a reasonably efficient way to apply that cranking impulse at the ascending node. So it's desirable, of course, to do that, but it's not always possible to do it. But the key result of this lecture, and let's summarize like what we did, is that we defined a cranking impulse. So this lecture, this is sort of a summary of the starting point for all of this, which is we defined a cranking impulse. And then we use the definition of a cranking impulse to derive a relationship. So you could say we derived a relationship between the cranking angle and the two inclinations of the initial and terminal orbits. And then 3, we showed that this cranking angle is equal to the change in orbital inclination if, I should say only if, the cranking impulse is applied at the ascending node. Of the orbit. If it's applied anywhere else, it's not equal to the change in orbital inclination. And it's important that you understand that this is only for the case of circle to circle transfers. So this is circle to circle transfers. Let's say rotations. Orbit plane rotations. We didn't deal with the case of ellipses. We're only dealing with the case of circle to circle orbit plane rotations. And I think that's a pretty good place to stop this lecture. Next lecture we're going to actually talk about the construct of what happens when the impulse not only changes the orbit plane but also changes the orbital energy.